Love how I say that. Is that how every video starts?
No, we were trying to test
Good afternoon. Okay. Usually follow up with that. You're funny. All right, guys. Well, just got back from orthopedics with Eve. She does have a fractured ankle, so you can tell she's still happy as ever. But she got to pick her colors of the cast, of course. Got blue with purple stripes, so pretty fun. But yeah, at least no more crutches. At least she can walk around on that thing, so that's good. Yeah. But, well, yeah. So exam this week. Exam on Wednesday. If you want to go to that review session, that's tonight, 7:30 in 102. Right? Is that where it is? Just right over there. Those of you that have gone, or is it down below? I don't know. Whatever room it's normally in. It's in one of these four. I think is it down below? It's right over there. That one? Yeah, I think so too. Okay. All right. So that's it for this week. The no lab. Yes. Okay. Any questions about this week or what's going on? Okay. So today's notes, we start what'll be the new material on the exam, on the final exam. So there'll be somewhere around 45 to 55 points of new material on that, as well as the rest out of the 150 on cumulative material. Okay, so that'll be what the finals looking like. But this stuff we're starting right here is the first bit of that new material on the final. Okay, there is a study guide for that on Canvas in that last module that has the final exam. So, and it does narrow things down a little bit. If you didn't have me last semester, that really all the study guide says for the cumulative stuff is everything that was on the previous study guides. That's what you can limit it to. Okay, like the study guides normally will say this is stuff to focus on, but you need to know everything. That's not the case for the final. Okay, the final is whatever I had on those study guides. That's what you can limit your studies to. Okay, for the cumulative stuff, and then I have a kind of a regular study guide there for the new material, and then that's kind of the same as the other ones. Like focus in on the stuff I have there, but know everything on the slides. Okay, so that's that. I know it feels early to start thinking about that, especially when you have exam 5 coming up, but it is, yeah, it's worth 150 points. So it does have the ability to change your grade quite a bit, either direction, right? People have been able to kind of push their grades up over whatever threshold that is that they're trying to work on just with the final exam. Yeah, so definitely something to start thinking about once you get done with exam 5 and start studying for that. So, okay. All right, guys. Any questions about any of that? All right. Okay. Well, today we're going to get into the more of the physiology of all those little structures we talked about last time in the kidneys, and that's really all about the production of urine. So it's just kind of a cool little artistic rendition of what the kidneys would look like on a microscopic level, right? We can see the little Bowman's capsules there, all the little afferent, efferent arterioles, all the little blood vessels that go throughout. Okay, so all right, we're going to dive right into this. So we'll talk about filtration. Filtration is what the kidneys do, right? So filtration occurs in the glomerulus, right? So that's that little kind of a ball of capillary beds that is surrounded by Bowman's capsule, right? We have somewhere around 1.2 liters per minute of blood flow going to our kidneys. All right, we talked about these numbers before. That's 1,500 liters per day or 400 gallons of blood flow per day. But then the amount of plasma that's actually filtered out, right? The stuff that comes out, we talked about that too. As we said, it was around 50 gallons before. If you do it like this, about 120 to 125 mils per minute, which is 180 liters per day. Okay, and this number, we'll come back to this number because this one is important. But our total urine production is only 1.8 liters per day. All right, so if we compare this number, 180 versus 1.8, that means that we bring back 99% of that fluid that gets filtered out. Right, there's really just 1% of the fluid left that gets pushed out of our blood into those tubules. Only 1% actually makes it all the way through to the collecting duct and out the ureter. Right, the other 99% gets pulled back at some point. Okay, But this is a lot of filtration, right? There's a lot of fluid that's getting pulled out of the blood. And so there's some anatomical things that help us do such a great amount of filtration. Number one is the large diameter short renal arteries. All right, so this increases flow. So we get a lot of blood flow going to the kidneys, right? And we also get a lot of hydrostatic pressure. All right, so the blood going into that glomerulus is under high pressure for a small capillary bed like that. So that squeezes a lot of fluid out when it gets into that glomerulus, right? That increases filtration. Okay. We also have the situation where the blood going into the glomerulus is in a bigger vessel than the blood exiting the glomerulus, right? So the afferent arteriole is larger than the efferent. What that does is that increases flow and hydrostatic pressure, right? It's like we send a lot of fluid into it, but then there's kind of a backlog on the other end, right? It kind of slows down the flow, increases the pressure. So that helps us squeeze a lot of fluid out too. And then it's also a very special type of capillary bed, very leaky, fenestrated capillaries, the ones that have big holes between those endothelial cells, right? So there's a lot of space for stuff to squeeze through, right? So we got high pressure, we got kind of a backlog in the flow, and we got holes in the capillaries themselves, and so we can squeeze a lot of fluid through this. That's how we get such a large number here for filtration. Okay, so what the stuff that comes out, we'll call it filtrate. Okay, what we actually have in there is we don't have any blood cells. We don't really have any proteins, right? So we don't get red blood cells very often. We don't get white blood cells very often. And we don't get large proteins, right? Because the holes, even though there are holes in the capillaries, they're not that big. They're not big enough to squeeze those things through unless there's some kind of a problem. And so really it's just, really just water and small things, okay? Small molecules, and we'll talk about some of those. So it looks very similar to our plasma, right? To the water portion of our blood that doesn't include those cells and proteins. Okay, all right. So this number, I mentioned it last time, GFR, or glomerular filtration rate. A normal GFR is the same thing as that number we just saw on the previous slide, that 120 mils per minute. Okay, that's just how much fluid is getting squeezed out of those little capillaries in the glomeruli per minute, right? And so this is a very good marker of the health of your kidneys. Okay, and there's some different ways that we can measure it. We'll talk about some a little bit later when we get to that towards the end of the semester. But yeah, once it gets below 60, then we start having kidney problems. Okay, so again, there's that huge range that's from normal function, and then there's this big space in between that's not necessarily normal, but it's not problematic either, right? But then once we drop below 60, then it starts becoming problematic for your physiology. Okay, so some things change this kind of continuously, right? So if for some reason we have an increase in systemic blood pressure, right? We get really stressed out, we clamp down all of our blood vessels, we start exercising, something like that, things that can increase our blood pressure systemically, that's going to increase our GFR, right? Because that's just sending more high pressured blood into your kidneys. Okay, we don't necessarily want to urinate more when we're stressed out or urinate more when we're exercising, probably the opposite, right? So the body automatically adjusts for that by constricting the afferent arteriole, right? That one that's sending the blood to the glomerulus. If we shrink that down, then we're going to send less blood into the glomerulus, and that can kind of readjust our GFR back down. Okay, this myogenic thing means really it just means like a reaction of the smooth muscle around the glomerulus, around that afferent arteriole. When it senses high blood pressure, it kind of squeezes down against that to kind of go against it. It's kind of like a reflex almost of the smooth muscle. Okay, if it goes the other way, if we have a big drop in systemic blood pressure, then that's going to decrease our GFR. Okay, that could be problematic as well. We're not filtering enough blood. Okay, so the way that we deal with that is we do the opposite. We dilate the afferent arteriole. That's going to send more blood into the glomerulus and try to get that GFR back up. Okay, we talked a little bit about shock a while back. We talked about the vascular system. In cases of shock, remember, there's one common thing that underlines all type of shock. Who remembers what that is? What's kind of the root cause of all shock? Okay, could be blood loss. Yeah, there's a large decrease in blood pressure for some reason. We don't have enough blood flow for some reason, right? So we have a decreased blood flow to our vital organs, and that's what shock is, right? It can be because we lost blood, can be because all of our blood vessels got too big, right? Like an anaphylactic shock. Could be because our heart's not pumping enough, right? So we don't create blood pressure. Could be multiple things, but the bottom line is there's some issue with not enough blood flow for some reason. So in that case, that's definitely going to decrease our GFR, right? If we don't have enough blood flow to the kidneys, we have a decreased GFR. Okay. Other things that can affect GFR: dehydration, right? If we're dehydrated, again, that's going to decrease our GFR, and that's because we have low blood pressure, right? Really, so that's going to create low hydrostatic pressure in the glomerulus, and we don't squeeze as much fluid out, right? Okay. But then also we have a higher relative protein. Higher relative protein concentration. And so then that kind of makes it so we hold on to more fluid as well because of that higher osmotic pressure. Okay. And then this one is really related to what I just said there. Lower water concentration. It's going to decrease our hydrostatic pressure, so we push less fluid out. So yeah, so both shock and dehydration will do the same thing to our GFR. It'll drop our GFR so we don't squeeze as much fluid out when the blood goes through those glomeruli. Okay, questions on that so far? All right. Okay, so let's define a few terms before we get into what happens along the pathway with all of those different little parts of the nephron that we talked about last time. Okay, so we just talked about GFR, glomerular filtration. That's how much fluid gets squeezed out, how much filtrate we make. Okay, the other term that we need to be aware of and be familiar with is called tubular reabsorption. Okay, so reabsorption is going to mean this is everything that gets into the filtrate that we do filter out that we want to get back. Okay, so like something important like glucose, right? We don't really want to be urinating out our glucose, okay, because that's a valuable energy source, but it gets squeezed right through the capillaries when we squeeze that filtrate out, and so we have to actively bring that glucose back so we don't lose it. Okay, so when you have glucose in your urine, that's not normal. Actually, sometimes we will have some glucose in our urine, but it's not a normal thing. Okay, we see this in diabetics for sure because there's so much glucose in the blood that there's just too much for the kidneys to bring back. So some of it stays in there, but in general, that's not necessarily normal. Okay, and we have to use active transport to bring this back. Okay, so we have to use ATP to pump this glucose back in. Okay, but those proteins kind of have a maximal rate that they can pump at, right? So when in a diabetic with lots and lots of blood sugar, a lot of blood sugar gets into the filtrate, and those protein pumps can get maxed out, and so some of the glucose stays in there, right? So it's just too much glucose to handle, so some ends up in the urine. Example of this, my son Soren, I'm sure I've mentioned, has type 1 diabetes, and he was just diagnosed about 2.5 years ago now. But one of the things that was happening that we were trying to figure out, like what is going on with him, not necessarily with him, but just with our toilets. Actually, we kept getting mold growth in our toilets, and we couldn't figure out why. It was like we would literally like all this mold would like show up in the kids' bathroom, and then we would clean it, and then like literally the next day it would be back. We're like, well, what the heck why can't we keep our toilets clean? And that was one of the signs that was happening, because he was just peeing out so much sugar, right? And mold grows a lot better when there's a lot of sugar available. And so that was all like before he was being diagnosed. There were lots of signs that neither my wife or I picked up on, even though I teach about this stuff and she's a nurse. And guess it's different when it's your own kid. But yeah, we're both like, oh, why didn't we think of that? Yeah. But yeah, so that was kind of a weird one. Even the endocrinologist was like, really, we hadn't heard that story before. But yeah, it was definitely related to all that sugar he was peeing out. But yeah, and it is, what diabetic that has lots of high blood sugar will just pee massive amounts, right? So we would hear him like multiple times a night, wake up, and we would call it the fire. Here goes the fire hose again. Like just like hear so much, and that's just normal for someone with diabetes, because there's so much extra osmotic pressure in the fluid that it pulls a lot of water with it. And type 1 diabetics died of dehydration before the invention of insulin, before the invention of synthetic insulin. That's how they died. It was a fatal disorder. 100 years ago, people just died of type 1 diabetes, but now obviously it was one of the first kind of like life-saving / like miracle drugs. As soon as you started giving somebody insulin, they just woke back up and they came back alive. So it's pretty remarkable. But yeah, so that's that. So that's reabsorption. Okay, so stuff we want to bring back, right? Stuff the body doesn't want to lose. Okay, and then secondly, secretion. Okay, that's pretty much the opposite. This is stuff we want to get rid of. Okay, so a certain amount of stuff will get pushed into the filtrate when we in the glomerulus, but then we might want to get rid of more of that same thing. So we have to actively push some more of that into the fluid as it's passing through all those little parts of the tubular system. Okay, so this would be all waste products, right? And as well as pH balance. Okay, so those are kind of the three things we need to think of when we think of like, all right, how much of a certain substance would we expect to see in the urine? Number one is, does it get filtered freely? Does it go through the glomerulus freely? And then number two, do we pull it back? Do we reabsorb it? And then number three, do we secrete it? Do we add more of it? Okay, and the kind of the balance of those three things is what tells us how much of a certain substance will be in the urine. Okay, so all these things together will have an overall effect on the concentration of the filtrate and the overall volume of the urine. Okay, so we're going to start making our way through each section of the nephron. So we'll start with the proximal tubule, and with each one, we'll talk about what is secreted, what is reabsorbed, and then what kind of effect we see on total volume and total concentration of the urine at each step. Okay. All right, here we go. So we'll start out with the proximal tubule, right? So if you go to this little image there, you can see the part that's yellow is the part that we're talking about, right? So that's Bowman's capsule right there. That's the glomerulus, right? So it's the very start of urine production. Okay, so reabsorption, we said last time, this is where the majority of reabsorption happens, is in the proximal tubule, right? So what's reabsorbed? Definitely a lot of sodium, okay, via active transport. And when we bring a bunch of sodium back, water follows it, right? Because that creates osmotic pressure on the other side, outside of that, of the tubular system, and then that pulls water right with it, okay? So water is going to follow the sodium. Okay, and then any kind of nutrients that we don't want to lose, right? So the glucose, like we're talking about, amino acids, okay, and then obviously lots of water, right? And so this is 65%, so about 2/3 of the water that comes back here in the very first part in the proximal tubule. Okay, and then the same equivalent percentage of ions that goes with that water. So what's the overall effect on osmotic pressure? If we have a water going as well as an equivalent amount of ions, nothing, right? Because water and the ions go together. So there's no effect on the osmotic pressure or the concentration of the filtrate at this point, because water and the salts go together. Okay. Do we secrete anything here? We can secrete, which is also another way to say excrete, right? So we try to get rid of hydrogen ions here. If our body's pH is a little bit low and we want to try to get rid of some of those hydrogen ions, we can do some of that here. This can help restore pH. Okay, so our overall effect on concentration and volume here. So we have a large reduction in fluid and ions, right? So a big volume reduction. Right, so 65% of the filtrate that we started with is already back in the blood, back to the body. Okay, but no change in osmotic pressure, so no concentration of it yet, right? It's still that equivalent, it still looks a lot like plasma, right? As far as the concentration of salt versus water, still looks very similar to plasma. Okay. All right, so that's the proximal tubule. Give you another sec to finish writing that down. Questions on that so far? Okay. All right, so then the next part we get to is the loop of Henle. Okay, in the loop of Henle, there's this special kind of mechanism that takes place known as a counter current multiplier mechanism. Okay, long phrase, long kind of name for this, but the bottom line is it uses fluid flowing in opposite directions to kind of create this almost like whirlpool effect and pull a lot of extra fluid back. Okay, so we got to think about the descending limb and the ascending limb differently, right? So the descending limb is this side, ascending limb is this side, right? Descending, talking about D and A, talking about the direction of the flow of the filtrate, right? So it's coming down this way, right? And then back up this way. Okay, so the descending limb, as that filtrate is going down, the filtrate is increasingly hyperosmotic versus the blood. So if it's hyperosmotic versus the blood, what would that mean? We're losing as the filtrate goes down. Ions or water? Okay, water. Yeah, most people say water. Yeah, so if we're losing water, then yes, we're concentrating the filtrate there, right? We're not diluting it. That would be the opposite. That would be like adding more water to it or pulling salt out. We're doing the opposite of that. We're concentrating it. We're just pulling water out, so it becomes very concentrated. Okay, and then on the ascending limb, it's the opposite. It becomes increasingly hypoosmotic versus the blood. Okay, so we could do that one of two ways. We could pull water out, right? Or sorry, we could add water to it, or we could pull salt out, right? One of the two. We'll see what we do here in a second. So when we think about the descending limb, this is going to be highly permeable to water. Okay, but no sodium is moving when the filtrate's going down the descending limb. Okay, descending limb is going down, water is getting pulled out. Okay, that's why it's becoming more and more concentrated until it gets to the bottom of that loop. Okay, and then it comes up and it makes this turn here, starts going back up. And now the opposite happens. Now we have all these sodium active transport pumps that are taking the sodium and pumping it out of the filtrate back into the interstitial space, back out here, right? So the space around the tube. Okay, but in this case, normally when we do that, when we did that in the proximal tubule, water was able to just follow it, right? But in this case, that ascending side is completely sealed off from water, so it doesn't happen. So it's impermeable to water. Okay, so we're going down on the descending side, water's getting pulled out, but sodium's not moving, right? Then we go back up the ascending side, water can't get out, but sodium's getting pumped out actively. Okay, so the result of this is that interstitial space around the loop of Henle, it becomes very hyperosmotic. So the bottom part of the loop, all that space around the bottom part of the loop is very hyperosmotic. We have lots of salt down there and not a ton of water, right? So we have high osmotic pressure down at the bottom of that loop all around the interstitial space. Okay, so the overall reabsorption here is another 15% of both water and ions. And since they kind of, even though one side moves water and not salt, and the other side moves salt and not water, they kind of balance each other out, and we end up not really changing the concentration of the filtrate here, but we still have given back another 15% of that fluid that was filtered out initially. Okay, go ahead, Mallory. Yeah.
If the descending limb, is saying like inside is hyperosmotic or the outside?
Yeah, they actually will match, and we'll see it in a couple slides that osmotic pressure will be similar on the inside as it is to the outside. And there's a reason for that, but we'll get to it here in just a second. Yeah. Okay, so this is kind of walking us through this idea of the countercurrent multiplier mechanism. Okay, and remember there were those two different types of nephrons in the kidneys, right? There was the cortical ones that just have those small little loop of Henle that just dips down into the medulla a little bit. And then there's those juxtamedullary ones that go super deep, way down next to those collecting ducts and then way back up. Okay, this is really only happening. This mechanism is really only important in the juxtamedullary nephrons. This is one with the really long loops of Henle. That was only about 15% of our total nephrons, right? But they have an important role to play, and it has to do with this. Okay, so take a second and just to recap what you guys just talked about, just kind of label what's moving in and what's moving out of the different parts there, and then just answer the question there on the top. Where does sodium come out? Okay, go ahead. Talk about that with your team and answer that question on your clickers.
That brings me back to this question. When you said like for this, you said you were talking about the juxtamedullary last time, and it was hard because I didn't really know the physiology yet, so I couldn't really understand it. You're saying if the glomerulus is closer to the cortex medulla junction of this one, right? The juxtamedullary, but you said that the closer to juxtaglomerular ones. Did you mean the juxtamedullary ones?
This one's closer to there, right? It's just lower down. This glomerulus is closer to that. Whereas this one's further away. That's
So this line right here?
Yeah.
This junction?
Yeah. It's just like
But is that for this type of?
that part's not as functional as the long loop is. No, it's just more of like visually identifying it.
Is that distinguishing between these two types
They are different. Yeah.
with the length of how close they are?
Yeah.
Okay,
Yeah.
I think maybe.
Yeah. It doesn't have a major functional role like the
So
long
it
loop
actually
does.
doesn't really apply to this because this is talking about just the dip part,
The
not
loop.
really how close.
Just the loop
The
part.
loop
Yeah.
of the juxtamedullary
Yeah.
and not the glomerulus like difference.
Glomerulus is just closer. It just sits down further on the long ones. But that's it. Yeah.
Thank you.
Yeah. All alone today over there, huh?
Is hyperosmotic versus fluid, like why? Like it just has a lot of the solute there,
Because it's
so the
losing
water's
water.
going in.
So as water comes out of it, then it's becoming more and more concentrated. Sodium stays in, water goes out. What part we haven't got to yet is the vasorecta is there too, and that picks up the water that's coming out. So that's why it's
Wait, so in this section going down, it's
Mhm.
losing water, which
Losing
is
water.
why it's hyperosmotic compared
Yeah.
to flood.
why it
But then
becomes.
when it goes up here, it gets the water again.
No, it just loses the sodium at that point. Kicks sodium out. Yeah.
Oh, because it's not permeable to water.
Yeah. Yeah. So they kind of balance out. Yeah. All right. So just send in that answer there. Where does the sodium come out? All right. Anybody else? Okay. All right. So about 95% of you are saying C is where the sodium comes out. So I would agree with that. That's the ascending side. Okay. So A there is just talking about this fluid flow in opposite directions, right? So we see the fluid going down, fluid going up. Okay. These are like microscopic little tubes. So these tubes are really right next to each other. Okay. And then we'll see, I'll show it just real quick, then I'll bounce back to this slide. We see also that the vasorecta is right next to these tubes too, right? So that capillary bed that was right there. So we have the vasorecta actually sending fluid in the opposite direction of the tubes too, right? So we see this going down and this going up, right? So we have opposite direction of fluid flow between the two parts of the, where the filtrate is, but then this is opposite on both sides as well, okay? And so with this two different systems with fluid flowing in opposite directions, it pretty much helps to pull fluid or salt out, depending on which side we're on. Okay, kind of just think about, I think the easiest way to think about it is kind of like these little whirlpools that happen like inside of these nephron loops, and that water flowing in or fluid flowing in opposite directions just is able to pull more water out on the descending side and able to pull more salt out on the ascending side. Okay, so water is getting pulled out there under B, right? And then as most of you guys said, sodium is getting pulled out here under the ascending limb. Okay. Yeah, and so it kind of shows it over here. And so the reason that water is able to get pulled out on the descending side is really because of what happened on the ascending side. Okay. And so that's why when you look at this little image, it says start over here. Okay, so if we're taking a bunch of sodium and putting it out in the interstitial space here, we're also putting it out over here. Okay, so and then the further down we are, we get lots and lots of sodium down here, right? So if there's a lot of sodium out here in the interstitial space, then that's what gives the interstitial space the osmotic pressure to pull the water out, right? Because it's going to follow that salt that's there, and so that's why these, when you see this described, it'll always start on that right hand side or on the ascending side, because it's the sodium that gets actively pumped out that sets up the gradient to pull the water out on the descending side. Okay, and that's kind of the basics of that. I know it's a kind of a intangible concept, that countercurrent thing, but as long as you're thinking of it kind of like as this whirlpool effect, and the fact that sodium coming out on the ascending side is really what's driving the water coming out on the descending side. That's pretty much what you need to know. Yeah, Zoe? It's just the way that the cells are set up there. Yeah. So the cells on the right hand side just have tighter junctions to them, or not really the right hand side, but the ascending side have tighter junctions, and so water can't get through. But then they're covered in these little protein pumps that can actively pump the sodium out, right? And then on the left hand side, the descending side, we don't have those protein pumps. But the cells are spread out far enough to where water can squeeze through if it's following osmotic pressure. So it's pretty much what it is. Yeah. And then all the way through the kidneys, whenever we have active transport happening, so a lot in the proximal tubule, and then here on the ascending side, those cells are much more ciliated because the cilia is where the little enzymes are, little proteins are that can pump the sodium. And so we'd see, if we were zooming in on these cells, the right side of that tube would look like really furry with a bunch of cilia pretty much, and the left side would look more smooth because they don't have as much cilia over there. There's not as much reason to pack in all those little pumps and to move sodium. So, okay, other questions on that? Olivia? Yeah. Nephrotic what? Syndrome? Does it say it on there? Okay, you're just putting it. Oh yeah, yeah. I don't know. That sounds like a pretty general term to me. Yeah, definitely. There's like nephritis and things like that, and really that just means like inflammation of your kidneys. So I would guess nephrotic syndrome would be like when you actually have some like, it's almost like a heart attack of the kidneys, like when part of your kidneys are dead and damaged. Because necrotic, any tissue that's necrotic means that it's dead, like the cells have died there. And so that would be my guess, that there's a certain portion of the nephrons that have died because of some chemical poisoning or something like that, or blunt trauma or something. It's my guess, but I'm not sure. Yeah. Other questions on that? Okay. All right. So the other key part of this, as I kind of already mentioned, is the fact that we have that vasorecta around those long loops of Henle. So as soon as this water comes out, it can get picked up by the capillaries and then brought right back to the general bloodstream. Okay. And then as soon as the sodium comes out, we do pick up some of it over here, but there's also other parts of the sodium coming out here, which is what's going to drop the interstitial space osmotic pressure or make it go up so high. And you can see that it matches wherever you're at, right? It's 900, 900, 900, right? And so it's pretty much matching the osmotic pressure there inside the tubular part, which pretty much matches the interstitial pressure, which matches that pressure inside the blood. Okay, but this is just kind of keeping fluid moving and picking up the stuff that's coming out. Okay, yeah. So that's kind of the basics of that idea so far. So let's go back to everything that just happened in the loop of Henle. Okay, descending limb, we know this is where water is reabsorbed. Okay, ascending limb, this is where salt or sodium is actively pumped out of the filtrate back to the body. Okay, and what is it that constantly drives this? Again, it's that countercurrent flow. Okay, and then also the important role of the vasorecta helping to pull those things that are pumped out of the filtrate back to the body, so we don't just oversaturate that area with either water or sodium. But the whole reason we're doing all of this is so we can create a very hyperosmotic space around the deep part of the medulla in the kidneys. Okay, remember this is those really long loops. And so if we look at the very bottom of the loop there, it's got very high osmotic pressure, okay? And then we have our big collecting ducts over here, right? This is where all those different distal tubules are plugging in. So the deeper we get, the higher the osmotic pressure is. And that whole reason for this countercurrent multiplier mechanism in the loop of Henle is so we can set up a really high osmotic pressure gradient there around the collecting duct. And we'll see why here in a second, once we get to that part. Okay, why do we care? Because we're setting up a hyperosmotic environment around the collecting duct, because in that collecting duct, that's kind of our last chance to pull water out of the filtrate and save a bunch of fluid. Because at this point, we've really only brought back about 80% of the fluid, right? That's 65 in the proximal tubule, 15% here in the loop of Henle. So if we lost 15% of the 1,200 liters, instead of 1%, we wouldn't last more than a couple of days. And so we need to get back a lot more fluid still. And we need to set up a strong gradient next to the collecting duct to be able to do that. And that's the whole reason that we do this big mechanism here. And this is studied across animal species. So certain animals that can survive off of just drops of water per day, like certain desert toads and different things like that, camels and things, they just have these incredibly long collecting duct, incredibly long loops of Henle. We get our osmotic pressure up to about 1200 or so milliosmoles at the bottom. Some of these animals can get up to around like 6000 milliosmoles, and they're literally just their urine production is drops per day, right? And so they're having to conserve every single bit of water that comes into their bodies, but it's necessary to urinate some, because that's how we get rid of waste products too, right? So urination is obligatory. We have to do it to get rid of waste products, but certain animals get rid of the tiniest little amount that can still allow them to survive. So, okay. All right, so then last step, after we get, so we're not quite last step, but next to the last step is the distal tubule. Okay, so reabsorption here, what things are we bringing back? We can definitely bring back some more sodium via active transport, but think about this as kind of the fine tuning. All right, so if we've already brought back enough sodium, we don't really need to bring back any more, then we won't do this. We can kind of shut this off, okay? And it's really only as much as needed by the body. Again, water is going to go with it, so there's no change in osmotic pressure here, okay? Secretion. We might need to get rid of some stuff. And here in the distal tubule, when we pull sodium back, we exchange that with potassium. So it's kind of a separate mechanism here that we didn't see in the proximal tubule and in the loop of Henle. That was just purely bringing sodium back by itself. In the distal tubule, it's an exchange for sodium and potassium. And so yeah, a little bit different. And then we can also get rid of some hydrogen ions here if we need to, if our pH in the body is too low. This can help balance our pH. Okay, so overall volume reduction, just a little bit, okay? Not really enough to even add to those numbers. And then overall concentration change, no concentration, because whatever sodium goes, water's allowed to go with it too, because it's permeable to water here. Okay, and then the last step, the collecting duct. Okay, so there's really no active transport happening here. So we don't have pumps that are pulling sodium back here along the collecting duct. So it's impermeable to sodium, kind of not really the best word for it, but we're not actively pumping sodium here. Secretion, nothing there, but the big thing that happens here is fluid, right? 19% of our fluid that we initially filtered out is brought back here. Okay, so big volume reduction. So it's very permeable to water here, and it passes by that strong concentration gradient, that was created at the loop of Henle. Right? So that strong concentration gradient, the high osmotic pressure down here, now the fluid is passing by that. So that's going to cause fluid to get pulled out as it's going by that strong concentration gradient. And so finally, the urine becomes hyperosmotic here because only water is going, salt is staying, right? So this is really the first place that this happens permanently, is we're losing a lot of water here and salt isn't moving with it. Okay, so 19% fluid reduction here, and we get concentration of the urine here. Okay, 2 clicker questions there in a row. So go ahead and talk about those with the people on your team. And let's vote on the first one first here.
Out in this sense.
On this side, water's coming out of there.
So there's a higher concentration of water, and then the vasa recta picks up the water,
Mm-hmm.
right? So then how does this create a concentration here? Is that because, like, what is?
It's mostly because we're pumping so much salt into the interstitial space out here. So we're kind of packing the interstitial space out here with salt because of this.
And that's why it comes back.
Mm-hmm.
Because of this.
Because, well, for 2 things, because the vasa recta picked up all the water that came out,
Okay. So there's
and
no
we
water
added
getting out
salt
there.
to it. And so, yeah, those are really the two key components.
Okay,
Yeah.
decrease in water, but increase in salt, which is why this is to go out.
Yeah.
Okay.
Yeah.
So in all those like survivor shows
Hmm.
where they like don't put water and they end up drinking their own urine,
Yeah.
with so much water getting filtered back into their body, would they get any water from that?
Yeah, yeah, it's still mostly water, what we pee out for sure. So it definitely it's something for sure. It's better than nothing. Yeah, it's very concentrated. Right? So it's yeah, it's got a lot of salt in it and a lot of nitrogenous waste like urea. You know, and so it's disgusting, but it does have fluid in it. So it's yeah, yeah. I'm sure drinking too much of it would be toxic to you, but
Yeah.
yeah,
Probably if you're at that point, there's probably not too much of it to drink.
yeah, totally. Yeah, exactly. Yeah.
I know. So we were talking about concentrations, and it reminded me of one of the lab or one of the lecture quizzes where it said that like it talked about the absorption of monosaccharides and amino acids.
Yeah.
And I put Na plus and Na plus, but the answer was K, was potassium
Hmm.
for amino acids, and I was just
Oh,
wondering.
it shouldn't have been. That was my
Okay, that was
mistake.
just-
It should be sodium. Yeah.
Okay.
Yeah.
Okay, thank you. I was so
Yeah.
concerned.
I'll check that. I must have did the key wrong. Yeah. Thanks. Yeah, it was the one that I fixed. Yeah.
So it's we're like, what are you talking
Yeah. Yeah.
about?
Like I did not. Yeah. That's it. Yeah. All right. Go ahead and send that in if you haven't yet. A couple more people. Almost an even split between A and D. So talk to the people on your team because it's almost at 50, yeah, 45% of you saying A, 55% saying D. So talk about it again and change your answer if you need to, but try to convince your teammates of your answer. All right, change your answer if you need to. All right, we're at 66-34 now. We're closer. Majority of you saying D. So D is the correct answer. The key word is permanently, right? Because in the loop of Henle, we do concentrate on the way down, but then we kind of correct that on the way back up. So overall, there's really no change in osmotic pressure by the time we get past the loop of Henle. But then in the collecting duct, we're just only water's coming out, salt stays. And so that permanently concentrates the urine there. Okay, go ahead. Talk about this one with the people on your team and vote when you're ready. All right, about 10 more seconds. Go ahead and send your answer in. Make sure to hit the send button. All right, I think there's about 7 more of you that need to send it. Make sure you hit the send button with this type of question. Okay, there we go. There's everybody. Yeah, so about 2/3 of you at least, a little more, are saying D and E. Okay, so oops, the collecting duct and the descending loop of Henle. So these are the parts where sodium does not move. Sodium can get pumped out of the distal tubule, definitely gets pumped out of the proximal tubule. and it gets pumped out of the ascending loop of Henle. The other one's only water moves and not sodium. Okay. All right, so here's what I want us to do for a sec. So there's 2 slides here that kind of recap what we just talked about with each of the different steps. Okay, so this one has the proximal convoluted tubule. Next one, the descending or the loop of Henle, and then this one shows the distal convoluted tubule and the collection duct. Okay, so I want you to walk through those with the people on your team, fill in what's going on there under each one. Okay, and then we'll come back together here in a few minutes and wrap it up.
Yeah, sodium nutrients, water. 65%.
Change out a lot of pressures. No, there's no change.
Yeah. So then would it be isomonic?
Yeah, I think it is.
Just anything that's brought back out of the ear and back to the body. Yes, reabsorbed.
Oh, okay, so it's just water.
I'm not sure which part you're on, but yeah, that's just, yeah. All right, guys, let's go ahead and come back together. Okay, so let's start here in the proximal convoluted tubule. Okay, big thing that's reabsorbed here, right? Salt and water, most of it, right? 2/3 of it comes back here. And then what else do we bring back here? Nutrients, yeah. So glucose, amino acids. And one of your classmates just notified me that on the last quiz, there was a question, though actually the one that I added. So if you took it early, if you're one of the 12 that took it early, then you didn't see this question, but the other ones did, which was which ion's concentration gradient is used to help bring glucose into the body in the intestinal tract and amino acids. They both should have been sodium. Okay, I think one, yeah, I just messed the key up. Yeah, so just want to make sure. Yeah, so both. I think one said potassium. Yeah, so just want to make sure you guys knew that before the exam on Wednesday. They both should be sodium. Amino acids and glucose both uses the concentration gradient of sodium to get into our intestinal cells. Okay, glad I haven't fixed it yet. She just, yeah, one of your classmates just told me right now, and I didn't realize that was an issue. So, yeah, I will fix it though. Yeah. Okay. All right. So yeah. So proximal convoluted tubule there. So overall change in osmotic pressure of the urine, nothing here, right? But volume reduction is major, right? 65% of our volume reduction happens here. Okay. When it comes to the loop of Henle, descending, we're reabsorbing water. Ascending, we're reabsorbing sodium. Mechanism for this was that counter current multiplier mechanism, right? The whole purpose for this was what we talked about, setting up that hyperosmotic state around the collecting duct. Right, so it's kind of setting us up for later. So in that collecting duct, we can then pull back a bunch of fluid. Okay, so overall change in osmotic pressure of the urine is none. All right, overall volume reduction is, yes, about 15%. Okay, questions about those first two parts so far? Okay, give you another sec to finish writing that down. Some of you took a big risk today and you wrote that down before I showed it to you. Others of you weren't feeling risky. Okay, all right, ready? No, not quite. Okay, all right. Okay, here we go. All right, so next one, distal convoluted tubule. What's reabsorbed here? Sodium and water. Again, water can follow the sodium, but this is different because it's the sodium is exchanged for potassium. Okay, overall change in osmotic pressure of the urine, none. Overall volume reduction, not enough to really even count as a percentage here. Okay, and then finally the collecting duct. This is where most of our, it's just water, no sodium. Okay, mechanism, we're using that same gradient that was set up by the loop of Henle. Okay, so we changed the osmotic pressure of the urine. Yes, here we finally have a large increase in osmotic pressure. Okay, and then a large volume reduction as well. The other 19% to get us right up to that 99% of the total filtrate that's brought back. So we're just left with that 1% of the filtrate that we urinate out. Okay. All right, the last slide here is just kind of kind of a recap of the whole thing. Kind of a good one just to check out. We'll get to the hormone involvement here later, but this one shows ADH, it shows aldosterone. We'll kind of get to how those affect it later, but this one kind of recaps everything nicely. All right, guys, have a great rest of your day. We'll see you on Wednesday for the exam.